To continue today with Swastik Kopparty. Swastik recently moved to Toronto, and he's going to speak about tensor ranks in price of multilinear forms.
Great, thanks. Okay, so what I'm talking about is somewhat old. It's from 3 or 4 years ago, but nobody has read it, so it's new. This is joint work with my former PhD student Abhishek Prashandi, Prahlad Harsha, Puya Hatami, and Mrinal Kumar, my former PhD student. Okay, so this paper has 2 results in it. I'll focus more on one of them, and I will do things slowly, and I will try to do a lot of some proof. Okay, so here's what the setting is. We have I'll focus mostly on three-dimensional tensors. So we have an integer k. We'll be looking at f2 to the k. Okay, and I will consider a trilinear form P of x, y, z, which I mean, it takes in 3 elements from f2 to the k, and it outputs something in f2, and it's trilinear. So it's presented by a 3-dimensional k by k by k matrix of entries from f2. Okay, so I mean, and it so underneath are k cube coefficients of the tensor. And the quantity that we want to study about the multilinear form like this is the bias of it. Okay, and this is, we plug in random values x, y, z, and out comes a bit either 0 or 1, and we look at what's the probability of 0 versus the probability of 1. So I'll write that down. This is the bias of p. This is the expected value under x, y, and z coming uniformly from f2 to the k of -1 to the bias, -1 to the p of x, y, z. Okay, so whenever the value is 0, it comes out with this is 1. Whenever the value is 1, this thing is -1. So it measures the 2 of them. Small bias means the output is close to 50-50 balance. Large bias means it's imbalanced. And good. And so this quantity, we want to know how it looks for a typical P. This is one question that we look at. So what is the value? Yeah, how big or small is P for a random? Oh no, it's bias of P for a random P. This is one question that I want to look at. And the second is, okay, so I'll say straight away, and it should be expected that bias is small when P is chosen at random, because bias being small is some kind of pseudo randomness. P being random is random. So how big or small is bias of P? And the kind of theorem that we'll prove is that the bias of P is small with very high probability when P is picked at random. And yeah, and from this. We will get, we'll see that a random trilinear form has low agreement. And by low, I mean half plus 2 to the minus omega k. In fact, 2 to the minus 0.99 k. With quadratic polynomials in 3k variables. And this is the kind of low correlation with lower degree polynomials that is.
What does it agreement mean?
Agreement is the number of points of agreement. Now, the agreement is having the same value, and by agreement of a polynomial with another polynomial, I mean the fraction of inputs on which the values have the same output. So having, I mean, half is something you either 0 or 1 is going to have agreement half, and this is going to have only half plus a tiny bit more, and this is basically the smallest possible for this. So it says that if you're looking for a function, and people are looking for this function, but if you're looking for a function that has low agreement with quadratic polynomials, then you can find one amongst the trilinear forms. Which one to get one explicitly is a big question, but we don't know how to do that. Yes.
You said this is optimal, so is there always a quadratic guy that beats his bias by a little bit?
Yes, beats by a little bit. Yes, just because trilinear 0, you'll get 0 will always do it. because if in a trilinear form, if one of the three inputs is 0, you already have a little bit extra agreement over the standard half. And it will be half plus maybe 3 times 3 divided by 2 to the k. So it's already, so 2 to the k, I meant to say 2 to the minus 1. Okay. If it was 2 to the minus k, then that would be for sure optimal. But this is only 2 to the minus 0.99k, but it's in the ballpark of that. Okay, so this is one statement. And the other statement that maybe I'll spend less time on is that, how this bias relates to other notions of pseudo-randomness about the tensor. And so it's a connection saying that bias small implies tensor rank of P is large. Okay, but large is not so large. If the bias is smaller than is very close to 2 to the minus k, say, which is about as small as you could hope for, then the tensor rank is slightly more than k, 1.1 times k or 1.5 times k. It will give bounds of that quality, which are not record-breaking bounds. The best known, first of all, there are tensors whose tensor rank is the omega k square, and finding one explicitly is a big open question. The known results for explicit tensor rank lower bounds are well, maybe 2 times k roughly, but over F2 there is a 3.52 k lower bound, and this so our results recover that through an argument based only on the bias. So the only feature of there's an explicit tensor. The tensor is the trace of xyz, where you view f2 to the k as f2 to the k, and look at the multiplication and trace map, and that has the smallest possible bias amongst all trilinear forms, and that alone is enough to imply that its tensor rank is 3.52k. Okay, so I will say a bit about this in the talk. Okay, so these are the kinds of questions that I'm looking at. Bias, and there's a big tensor rank connection in how we do this.
So you recover the biggest, an explicit tensor with the biggest known tensor rank.
Yeah, that's right. That's right. Okay. So let me tell you a little bit about the strategy for studying the bias of P for a random. So, okay, and all these things that I said, I'm focusing only on 3-dimensional tensors. Similar results hold for larger tensors. These results continue to be interesting for higher dimensions. These results completely stop being interesting because for 4-dimensional tensors, for example, there are very easy to construct explicit tensors with tensor rank k square, where k cube is the target and k square is easily achievable. But these kinds of connections, the best you could hope for, the best inference about the rank you can get out of small bias is again linear in k. So I mean, while there is a tight connection between this, it is not enough to prove interesting things. From the point of view of the question, give me an explicit tensor with high tensor rank. Okay, so want to show the biases. Want to show that bias of P is small with high probability. Okay, and the kind of result we'll show is that the bias of P is not just small, it's not just small with high probability, it's small with super high probability. It's so super high that so we'll show that bias of P is small with super high probability. Not only that, the agreement of P with any function is very close to half with super high probability. This will allow us to union bound against all quadratic polynomials and show that a random polynomial also has agreement only half plus something with all quadratic polynomials simultaneously. So it is important for whatever I'm doing to show that bias of P is small with very, very high probability. The very, very high probability is important for the application. So yeah, to actually show this thing about quadratic, I need to say something not just about bias of P, but bias of P plus a quadratic. But I'm not going to do that. I'll just do it with this. With high probability, I'm changing that to very, very high probability. Okay, and the strategy for this is, so this is related to a strategy of Ben Eliezer, Hode, and Lovett from 2012, which is to look at to show that the bias is something small, is to look at its moments. Okay, so here we're going to look at. So we'll focus on the following expression. We'll just do some algebra expanding and studying it a lot. So so let us study the bias of P to the power T. We look at the expected value of this over a random P. Okay, and we'll apply Markov's inequality with a large value of T. Okay, and then this will give us, if we can show that this is small for a large T, then this will give us a good bound on the bias, being the probability that the bias is large. Okay, and apply Markov. Okay, so now I'm going to do just a calculation in front of everyone, and hope if it goes well, then we will see a connection to some tensor rank kind of questions. Okay, so what is the bias of P? It is, okay, let me move this up. Bias, so I'm looking at the expected over P. This is expected over P, bias of P. So bias of P is expected over X, Y, Z minus 1 to the P of X, Y, Z. This thing to the power T. So I have inside the expectation to the power T. So the way to study that is to open it up. Okay, so I'll just open it up. This is expected over P, then expected. So open it up means just make T different copies of this, each with a different index I, and just multiply them out. So this is expected over X1, Y1, Z1, X2, Y2, Z2, and so on, up to XT, YT, ZT of minus 1 to the P of X1, Y1, Z1 times minus 1 to the P of X2, Y2, Z2 dot dot dot. So this is just a massive exponent up there. Okay. And when you see two consecutive expectations, the first thing you should do is just swap them. And then right. So we swap them. And we get expectation over X1, Y1, Z1, and so on to XT, YT, ZT. Expectation over P of, now this, let me interpret this a bit. This is P of X1, Y1, Z1. That's the same as the inner product of the P vector. I write P as a very long vector of length K cube and X1 tensor, Y1 tensor, Z1. The rank 1 vector made out of the X. And this is the inner product of P with X2 tensor, Y2 tensor, Z2, and so on. So I just rearrange that a little. Minus 1 to the inner product of P with summation Xi tensor, Yi tensor, Zi. This inner product you interpret right. This is K cube, this is K cube coordinates. Good. So this is what I'm calculating. Now, the most basic fact now about expectations, and in this whole world, here's a really basic fact that's if you look at expectation over a random vector X minus 1 to the V dot X, what is this? This is either 0 or 1. This is 0 if V is non-zero, and this is 1 if V is 0. It's most of the time it's 0. Occasionally it's 1. It's 1 whenever V is 0. This is just a basic fact about how you take inner products with biases of a random linear function, basically. Or biases of a linear function. So this is exactly that form. P is picked as a uniformly random vector, and it's inner producted with some particular vector. And so what's of interest is whether it's 0 or not. Okay, so this is equal to exactly the probability over X1, Y1, Z1 all the way up to XT, YT, ZT of whether summation Xi tensor Yi tensor Zi equals 0. Okay, and this is the question that this is the kind of question we want to study. We have picked 3T random vectors X1, Y1, Z1 all the way up to XT, YT, ZT, and we'll put the sum of their tensor product in this way. and we want to know what is the probability that this is 0. And our hope is that it's very, very small. If this is very, very small, remember, this is just the, this was just an equality all the way from there. So if this is very, very small, then that is very small. And then the probability the bias of P is big is also small. Okay, so let me tell you what the theorem statement is for this. The theorem statement is for that. And for just the bias. And then I will start playing with this, and we'll see some more interesting statements. Questions? Okay, so the theorem statement is that the probability over a uniformly random P that the bias of P is greater than 2 to the minus 0.99k. 0.99 is shorthand for 1 minus epsilon. Is, so that's big, is small. At most 2 to the minus 0.01 k cube. So 0.01, it would have been nice if 0.01 was 0.99, but but it's 2 to the minus omega of k cube. It's very, very small. So even if you, and this has the feature that if you union bound it against 2 to the k square different quadratic polynomials, this is still small. So that's why it's okay, even though it's 0.0. This is the first theorem about trilinear forms. There's a similar theorem for D-linear forms, where k to the 3 becomes k to the d. This connection is fine, but you also need to assume, so for general D, for D-linear, need to assume that d is smaller than 2 to the 0.01 k. Fine. Okay, this is, and then k cube goes to k to the d. So as long as you're not talking about very high dimensional tensors with very short sides, which is just a bizarre thing to look at, because those are anyway, those are very bizarre things to look at. Okay, so this is one theorem. That's the final theorem about the bias being small with high probability. And the intermediate theorem that is the statement about this is that the probability. So let me see. So if t is less than 0.01 k cube, no k square, then the probability that summation xi tensor yi tensor zi this is the probability over uniformly random this I going from 1 to t. The probability that this is equal to 0 is at most 2 to the minus 0.99 times k times t. And this is also, let me tell you one way this sum could be 0. If all the xi's were 0. And the probability of that is 2 to the minus k t times, so 2 to the minus kt. So this is roughly the same state. Okay, and this holds for as long as t is not too close to k squared. And taking this value of t and putting it into that Markov bound argument gives you this state. So this gives this immediate. Okay, so I'll now say a bit more about what you do with this, and then that reduces to some statement about matrices. And okay, so what I'm doing now is I'm taking this and studying it a little, trying to, with the intent of bounding the probability that this sums to 0. So what's the probability that this sums to 0? Okay, so the first thing I want to do is I will, so this 0 is not just a regular 0, this is a big 0. This is k cube, many zeros sitting there on the right. So I'm going to study a few of these zeros at a time. So I'll break the zi into its k coordinates and see that those k coordinates behave largely independently. Okay, so let's see that first. Good. So this is sum I going from 1 to t of xi tensor yi tensor zi. This is equal to 0. This is the same as for all j in 1 to 3 up to k, sum over all I going from 1 to t, xi, tensor yi, tensor zi sub j. No, the jth coordinate of zi, right? This is just a bit. This is a k by k matrix. I'm asking that this linear combination of the matrices ends up being the zero matrix. And I'm asking for k such linear combinations to end up being the zero matrix too. Okay, and all these are independent of each other because the zi1s and the zi2s are all independent of each other. Okay, so good. So for fixed x1, y1 all the way, x1, y1, x2, y2, dot up to x t, yt. So I'm not fixing the z's, but I fix the x's. For when all these are fixed, the probability over z1 up to zt, that summation xi, tensor yi, tensor zi is 0. This is the same as the probability that this happens to the power k. What's the probability that this happens? Well, what does it look like? It looks like I have a whole bunch of matrices, xi, tensor, yi. I have a whole bunch of matrices. I'm going to give random coefficients to each one of them and ask what's the probability that that linear combination ends up being 0. When I have a random bunch of vectors and I give them uniformly random coefficients and I add them up, what's the probability that that sums to 0? These are vectors. I have a whole bunch of vectors. I'm going to take random linear combination of them with 0, 1 coefficients. They're in f2 to the k. And I ask what's the probability that that random linear combination equals 0. So what's the answer? 1 over 2 to the k, sort of. What if all those vectors were v0? Then what's the probability that a random linear combination of v0, v0, v0 equals 0? Then it's half. What if half the vectors were v0 and half the vectors were v1? Then it's, well, v0 is some random vector and v1 is some other random vector. Well, the probability is, so when you take a random linear combination of all these vectors, what you get is a uniformly random element of their span. And the probability that the one you get is 0 is 1 over 2 to the dimension, 1 over the span. So 1 over 2 to the rank. Okay, so this is equal to something to the power k. What's the something? 1 over 2 to the rank. By rank, I mean dimension, right? Dimension of the span of x1 tensor y1, xt tensor y. And this whole thing to the power k. And that is, and yeah, that's it. Note, we've just been doing equalities all the way. This is just all algebra. There's no analysis. It is, but what we need to know is what's the probability, or we want to show that this probability is small. To show that, we would like to show that with high probability over the choice of x1, y1 up to xt, yt, the dimension of that is large. So good. So now we have a question about matrices, and maybe matrices we can do something. Questions about this? So I mean, everything was really equalities everywhere. So we really, so far nothing has happened. Okay, so I am now going to study this question. We take a whole bunch of random rank 1 matrices. What is the distribution of their rank, of the dimension of them, of the dimension of the space spanned by them? Okay, that's what the question is. So so we pick. So I'm writing this the setting again: x1, y1, x1 comma y1, xt, yt in f2 to the k, uniformly at random. What is the distribution of the dimension of the span of x1 tensor y1, xt tensor y2? Okay, and I'm hoping to be able to give a good answer to this for t's going as large as omega k square. Okay, because the space of all this is the space of matrices, k by k matrices, and within this here I want to the kind of statement I want to show is that very likely the span of x1 tensor y1 all the way up to xt tensor yt has rank very close to t, or has a dimension very close to t. And so now this gives us the next theorem statement, which and this is the theorem statement where inequalities will happen. Okay, so for t less than 0.01 k square, the probability that the dimension of the span of x1 all the xi tensor yi's t is less than something, or maybe 1 minus epsilon times t, probably that's quite small, is small, 2 to the minus, yes, tk, 0.99 tk. Is that what I want? First was 0.01, and this is t is this. My unit should, no, when t is small, I want it to be good. Okay, so yes, I think I messed something up. For t smaller than this, dimension of the span should be okay, what's the best I could hope for? And it's that. So let me see what the best I can hope for is. Okay, I think okay, maybe this is right. So there's something a little odd about what I wrote, which is that when t is very, very small, it's it's fine. Okay, good. I wrote with 1 minus epsilon t. Now okay, I'm fine. Sorry. Good. So this is the state.
1 minus epsilon 0.99.
1 minus epsilon 0.99. Yes, that's right. That's right. Right. Yes, good. Now, yeah. Right. This is the statement. And underlying this, and you can see why this is relevant, is the following. So, I mean, what's the chance that the dimension is not as big as t? Well, for that to happen, many of the xi tensor yi's should be in the span of the previous x1, xj tensor yj's. Okay. And that is the event, that is the probabilistic situation we look at. So fix a subspace U inside F2 to the k cross k. Okay, so this is a linear space of matrices. Dimension of capital U, I'll call it little u. Then what's the probability that a uniformly random x tensor y, this is over just x and y, that x tensor y, this is xy in F2 to the k, uniform, independent, lies in U. Okay, I want to say that this is small. No linear space contains too many rank 1 matrices. Being rank 1 is not so closed under addition. This is the statement. And it is at most 2 to the u over k divided by 2 to the k. Okay, good. And I now know what this should have been. Yes, this is t over k divided by 2 to the k. Yes, so there's always a 1 over 2 to the k component sitting there. Yes, that's what the statement is. So when u is very big, near k square, so let's say it's 0.01 k square, then this is just 2 to the 0.01 k divided by 2 to the k, which is still almost 2 to the minus k. So for u's going all the way up to nearly constant fraction of the space, this is a very, very small number. So it's very unlikely for a linear space of matrices that has less than constant fraction dimension to contain a rank 1 matrix, a random rank 1 matrix. So this is, so I'm now going to open up this theorem and prove things. So this is where the inequalities happen. Questions about the statements that we've been writing? And all these statements, I mean, what I said about three tensors, and it reduces to a statement of 2 tensors. They also work for d tensors, and they reduce to statements for d minus 1 tensors like this, about the random rank 1 d minus 1 tensors lying in a linear space of d minus 1 tensors. So I'm not going to, so this is the sort of the hands-on part of the talk where I will open up what it is that you need to analyze, and then it'll just give a flavor of what happens inside, and then I won't finish the proof, but I'll sort of tell you what it is that one has to do. Okay. So we have a subspace U, a linear subspace U of matrices. So yeah, how do you even think about these? So what I'm going to do is, so this is a K by K matrix, and I have a linear subspace U. I want to do an echelon form decomposition of the space U. So for that, out here is actually, this is the linear space U. It is, its dimension here is little u, and each element of capital U is K square long. Okay, so I took a basis of capital U, I wrote down all the elements here, and I do row operations and column operations, and I get an echelon form decomposition. And I order these coordinates so that it's row by row by row. Okay, so you understand what I did? So this is the K by K setting, and this is the K square by dimension U setting. Every element here is actually a matrix which is K by K. And I echelon form decomposed it so it all looks like this. So every element of the space U looks like there's some vector whose support possibly is everything. That's the first row. And then you add into that linear combination further matrices. The second matrix may look like this, along with everything down below. And the 200th matrix may look like zeros in the first so many rows, and then it has support over here. Okay, so this is what I mean by the echelon form decomposition. Okay, and this gives us the following. This gives us some shape for the space U. So I'm going to write that shape. Good. So I will let UI be the, okay, I'm going to gather some of these rows. I will gather all the rows whose pivot element, there are pivot elements in the echelon form decomposition. All the rows whose pivot elements lie in the first row, those I gather and call them one collection. So now I'm going to create these collections UI. So there's U1, U2, etc. up to UK. These all sit inside F2 to the K. These are linear spaces. And an element, good. How do you generate an element of U? To generate an element of U is to first pick which elements from UI, which elements from U1 you're going to take a linear combination of. So I'm going to, so in general, you're just going to take a random linear combination of all these elements. But I want to break up this part into the combination that you take of the first group, those which have the pivot in the first row, the part which comes from the second row, the part which comes from the third row, and so on. Okay, so cutting all that short, I will write down the shape of a general element of U. So we have linear spaces U1 up to UK. Dimension of UI, the sum of the dimensions of the UIs is equal to dimension of U. UI, the dimension of UI is how many rows in this decomposition have pivot element in the ith row. So the sum of all the the UIs together break up all the rows of U into all the rows of dimension U into partitions. So this is this, and a vector. Okay, and so we have these linear spaces, and we also get linear maps. So we get linear maps, I guess psi ij from UI. So for I less than j, it goes from the ith block to future blocks from UI to F2 to the K, such that an element V is inside U if and only if. Okay, V1 should be in, okay, the first row of V1 should be inside U1. So let me write that down. row 1 of V should be inside U1. The second row, row 2 of V should be inside, well, it should be inside U1, and it should be, in that case, it should be the element little u1. So row 2 of V should equal psi 1, 2 of U1 plus some element U2, which is in U2. Okay, and so on. So what's the so on? So in general, row I of, actually we should be calling it row J of V should equal, well, you've already picked what, you already picked which combination of the previous rows you're taking, because they made sure you had equality in the first so many rows of V. So the jth row of V should equal, let's take away the contribution of what you've already picked from previous rows, which is the sum over all I is less than j, psi ij of ui plus uj for some uj in capital Uj. And this is the echelon form decomposition that that every element of U looks like this. So an element V is inside U if there is a decomposition like this, where you have all the relevant little ui's inside the respective capital ui's, and there are these these spaces capital ui there. Okay, so this is a bit of an elaborate decomposition. Good. So maybe let me see if I can say something that enlightens this. What are we doing? We are picking a vector x tensor y. X is uniformly at random, y is uniformly at random. How could x tensor y is, how does it look? Every row is either, so let's first pick y and then we pick x. So we've picked y. Every row of x tensor y is either y or 0. Okay. Now, so let's, as we reveal the bits of x one by one, the row that you get is either the two options for the row that you get are either y and 0. So right, on the other hand, you've already the space U is such that you've already had to make some choices to check whether x tensor y lies inside the space U. Right? You have to pick the U1 that makes this equality, you have to pick the U2 that makes this equality, and so on. So after, so you've made a bunch of choices of the U1, U2, etc. At each stage, you reveal one more bit of x. At that point, you have to check whether there is a uj that makes this equality happen. Okay, and that uj has to be chosen. And there's a half chance that the uj that you want cannot be chosen. And why is that? Because right, so so the two different revelations of xi, namely 0 and 1, give you two different vectors which differ by y, right? Because that row y is either 0 or y. There are two different rows that differ by y. And if y is such that y does not lie in uj, then only one of those two can end up making this have an equality. So yeah, so to summarize, what we get out of this is that the probability, so fix y, then the probability that x tensor y, now this is a probability only with the random choice of x, the probability that x tensor y lies inside U is at most 2 to the minus, where you get a half dampening for every I where y does not lie in ui. So 2 to the minus number of I such that I call these j, I guess, j such that y is not in uj. And okay, so and this becomes so this is actually the only inequality step of the whole proof. And Yeah. So at this point, one needs to see how could I mean, so I have a space U. It comes with, after echelon form decomposition, you get a bunch of spaces U1 up to UK. And the quantity that you want to minimize is the probability over a Y. So probability over Y that this is small. Okay, so this is basically what one needs to minimize. So minimize, or not minimize. So I want to give an upper bound. So maximize over choice of U. I guess these are the dimensions now, right? The dimension of U1 up to UK, the probability over the choice of Y, in fact, the expected over choice of Y, 2 to the minus number of J such that Y is in UJ. And this is exactly the best upper bound you can get out of this method. And okay, and then it becomes some analytical inequality. And this analytical inequality has, so let me go back to the statement. So the statement is, you have a space U of dimension little u, and we are bounding the probability that a random rank 1 tensor lies inside the space U. There are two extrema for this. Let me tell you two extrema. One is capital U is of the form A tensor F2 to the K, where A is of dimension U over K and F2 to the K is of dimension K. So you could have, so the extrema U is A tensor F2 to the K. There's also another F2 to the K tensor A. Both of these give you equality in this bound. This is the tight example for both. Those two examples look very different from the point of view of how the dimensions of these echelon form spaces UI look. In the first case, the UIs are all A, and so they all have dimension U over K. In the second case, the first U over K of them have dimension K, and the rest all have dimension 0. And so whatever optimization we're doing here is a very weird kind of optimization. It has multiple extrema. Those are the only two extrema. And anyway, it becomes some, this becomes some inequality, which, yeah, okay, we struggled through with 2 pages of fighting. But at the end of it, it was, I mean, you have to keep in mind that there are two extrema. Yeah, and okay, so that helped the fight. Yeah. Okay, so that's all I'm saying now about the statement that with high probability over P, bias of P is small. Okay, now let me say something a little bit about if P has low tensor rank, then it has high bias. Or in other words, if it has low bias, then it has high tensor rank. Okay. Good questions.
Does it also work over other fields, or is it something special?
Good question. I think it works over all fields. The last bit of fighting is the only suspicious part. Everything else definitely works over other fields. Yeah.
Yes, it seems like you use a lot of independence, but could you say something about, say, X tensor X? If you want to say something about homogeneous polynomials, it's multilinear.
Oh, that's a very good question. So let's look now at a linear subspace of F2 to the K choose 2, maybe. And so it's a space of symmetric matrices, and you take X tensor X and look at this. So this proof strategy totally breaks down. Yeah, okay, so that's a good question. I don't know an explicit answer. So there is a result of, yes, this is called, yeah, there's a statement that talks about this. This is, it's a result of Kivash and Sudakov analyzing the ranks of inclusion matrices over FP. That's the.
But they don't some kind of tensors. You go 1 degree higher.
Right. So I'm not sure, but that statement has relation to this general question of yeah, you you have a space of polynomials, and you want to know how many points can they all vanish on, and the relationship between the vanishing set size and the dimension of the space of polynomials. That's the kind of question this is. So that would have implications about it. But as far as I know, there are many things unknown about that question. 6 minutes? Oh, okay. Well, good.
10 minutes.
10 minutes. Oh, thanks. Okay. Okay. So let me say quickly then this other statement. So this is if P of XYZ, as tensor rank P, then bias of P is at least 3/4 to the power T. That's what the statement is. So we originally had a proof of it from scratch. It's not very difficult. I guess I'm not writing a proof now, but it's not very difficult. It's about half a page of basically algebra. But now this statement also follows from Lovett's statement on the subadditivity of tensor rank. No, a subadditive of analytic rank. This is just the statement that so if P is of the form summation UI tensor VI tensor WI, where I goes from 1 to T. So since if P has the analytic rank of this is at most the analytic rank of this, the analytic rank is nothing but the bias in a different language. And the analytic rank of a rank 1 tensor you can find is log of 3/4 or whatever. So this immediately gives the statement. Although the proof of that is serious. Good. So this is what the statement is. What it implies is, it already has the ability to give super K tensor rank lower bounds. What I would really like to see is some implication that gives. So this is basically a question. Gives for 4-dimensional tensors. By the tensor rank be at least 1.1 times k squared, which is a famous open question. Do we know to give an explicit tensor whose tensor rank is slightly more than k squared? This we do not know how to do. Some implication about the bias or some property of P, maybe correlation with lower degree polynomials that gives this. This would be really, really nice. Let me also mention that, so I know that, so bias definitely is not enough. There has to be some other assumption about the tensor so some, so from the behavior of the form, from the multilinear form. This would be a really nice question.
Is the best known lower bound for a trace of XYZ W?
The tensor that is O of K. So it is, it has an abnormally low tensor rank. And trace of XYZ is also O of K. And this is an amazing result of Chudnovsky and Chudnovsky using algebraic curves with low genus and or way of high genus, but many points. Yeah. So this is this is something to keep in mind. Yeah, that once in a while tensor ranks are abnormally low. Right. So there are natural things to try. For example, the matrix multiplication tensor, if you look at its bias, it's already enough to imply super K tensor lower bounds. It gives 1.7, maybe 1.7 K tensor rank lower bound just through the bias connection. So one could consider the matrix multiplication is counting triangles. You could count tetrahedra in some appropriate high dimensional setting, but as far as we know, we were not able to get any implications to the tensor rank. So this, I think, is a really nice question. So a very nice open question is to give an explicit degree 3 polynomial which has low correlation with the degree 2 polynomials. The best explicit bound we know right now is correlation at most so find f of xyz or p of xyz. It's that agreement of P with quadratics is at most half plus 2 to the minus 0.9 K. This is so this is explicit. That's the issue with this question is to get it explicit. And so we know this with K over 2. And this comes from, yeah, there are a variety of things that give this. But one example of a function that does this is maybe XYZ, trace of XYZ, what was it? And yeah, there are a few more examples that have this kind of behavior. Okay, I guess with that I'm done. Yeah.
Because what is that? It's a trace of XYZ, or was this the inner product? XYIZI, sum over I do.
Oh, what does that give? That gives something. It is whatever comes from this Baba-Nissan-Szegedi argument. And that is something else. So maybe it's
Worse.
That is worse. It maybe it's 7/8 to the power K. And no, maybe it's 3/4 to the power K, which is 2 to the minus something times K. With some different constant.
Yes.
Yeah.
This also works for F3. So do you get tensor and low bounds?
Yes, everything I said works for all characteristics, but the quality of it decays. But for any fixed P, you will get tensor rank low bounds of 1 plus, I think 1 over P. That's times K is the kind of low bound you get. But none of this is record breaking for explicit tensors. It is just a connection between them, and it's the best you could hope for. Okay.
So yeah, so low bias gives high tensor rank, right? Meaning high analytic rank
Right.
gives high tensor rank.
Right.
Which makes sense, I guess, because random tensors have high analytic rank. That's kind of the intuition, right? Anyway.
Right. And that's the first statement.
Yeah, that is actually your first statement.
Right. And the second statement is high analytic rank gives high tensor rank, but tensor ranks can actually be much higher.
Yeah.
So it's not even in the same ballpark.
No, it doesn't actually.
Yeah, we don't even have, since we cannot prove explicit low bounds and tensor rank of that form, it would be nice even to have just an analytic quantity whose smallness implies the highness of tensor rank all the way up to K squared, and we don't.
But if you do if you would instead of analytic rank use slice can you use slice rank instead if you have high slice rank?
Well, we know examples like the diagonal tensor has the highest possible slice rank, and it's not remarkable in any way.
Some of the analytic rank, it's quite special in that. Like you would think analytic rank and slice rank are kind of similar,
right? And they are. Right?
No, you can do this something with slice rank. You cannot do this at all, like you're saying. Yeah,
They're comparable, right? Like rank and analytic rank are comparable.
yeah, I know, but with slice rank you cannot.
Yeah, but this is now we're caring about the difference between 1 times and 1.7 times, right? Yeah, so they are not that comparable, slice rank and analytic rank. They're just pretty comparable, right? Yeah, right. So they're not totally identical for all purposes. Yeah, that's the corollary.
Yeah.
Yeah.
Still, yeah. Thanks.
Okay, great. Thanks.